Okay, so for those of you, actually, so lecture 32, EE123. Woo! Okay, now I'm really into this. I want to show you one thing that we just did right now. We had a demo where we sent a packet through the ISS and was DGP'd back. This is a website that aggregates all the packets that are received by the ISS and are picked up by Earth stations. Okay, so it looks for packets received, and I don't know if you can kind of notice here. There's a school here symbol, and that's call sign. It's my call sign. And just to prove to you that, yep, that was received. And you can kind of see the messages over here. This is messages aggregated. And I think we'll have to go a little bit back. Oh, there you go. So KK6MRI was calling with AP DSP, that's the DSP class, was calling through RSOISS to KK6KJT, that's Frank. Hi Frank via ISS, that's the first message. The second message, I did pick up a station. I think that was this one that I picked up from there, but we had some technical difficulties where suddenly my audio stopped. Anyway, it was a poor setup, and I missed half of the pass. But still, we got three packets up, which is quite cool. So, yay. And Frank was able to pick up some other packets back too as well. So we tried to, oh, you missed this one? Right. Yeah. So that was the position. That's how they know to put the KK6MRI house symbol on Berkeley. This is basically a position packet. And I'm going to explain it to you today because today we're mostly going to talk about Lab 6B. Okay. Yeah. So that works well. That's pretty good setup. Again, I used one of these antennas that we built. This is did I show you this before? I did, right? Yeah, this is a measure tape antenna. You can open them like this. That we made in EE84. It took about an hour and 30 minutes of unskilled workers to do this with someone that already built one. So I'll say about 3 hours if you haven't done that before. Okay, so one announcement which I forgot to put. Some people ask for extension for this lab. I usually don't like to give extensions. You seem to be asking them quite a lot. But since there's a Part A and a Part B for Lab 6, I'm okay of you submitting Part A and Part B at the same time. Okay? That doesn't mean that today, frantically, you're going to stop working and wait till Monday to keep on working on both labs. Okay? There's a good reason why we give this 2 weeks. Okay? So keep on working frantically to get the modem because you're going to be working frantically to get the other stuff working too. Questions?
The Part A submission online right now is like a text box. It's not, you can't submit directly.
You will be fixed.
Yeah, I just want to be sure.
Okay. The other thing is that we really apologize, but there's some miscommunication on our hand, and the labs were not graded. We're going to go back and grade all lab 1 to 5. We posted solutions online. Frank? Yeah, all the solutions for the labs, our solutions, are posted now.
Right now,
yes?
all the labs are out of 0.
You what?
All labs are out of 0 right now. So
Out of 0?
yeah, so when they're graded on pre-courses, they're graded out of 0. So we don't actually know how well they know them.
They're not graded right now.
I mean,
Okay, we'll fix those. Yep. But lab 6, you'll have to also auto self-grade too. So and then that's it. Any more questions with that regards? Okay, so just in terms of what's going to go on. This Friday, we are likely to have a guest lecture that's going to give an application type of lecture, just to see, so you could see what you're actually doing in the class. It's probably going to relate it to computational optics. Okay. Next week, we've got Balin Sieber, who's the same guy that was on the video explaining about the software-defined radio that you got in one of the labs. He's going to come in, and I'm not sure what he's going to talk about, but every time I hear him, it's just, it's really the height of the lab. He does really cool stuff at us research. So you'll be able to see what he's doing with software-defined radios. Next week on Friday is the last midterm. One of the things we're going to put in the midterm is a question about the labs. Okay, there's going to be one lab-related question. So you don't feel that you just did this labs without actually being on top of that, asked that about it in the midterm. So I don't want you to complain. So we're going to ask you a question about the labs. Because you spend so much time on them, right? So it's the format could be it could be like stuff in material that's related to the lab that's embedded in the question. But there's going to be something that we've covered in the labs that is going to be in the midterm. The week after that, there's going to be the project presentation. We're thinking about splitting it into two, on a Thursday and a Friday. RTAs will post a poll online where you'll be able to give your availability. Okay? Just so it's manageable and also enjoyable. What else? So that's pretty much announcements. Any questions about this? Yep.
Projects are due day of presentations?
Yes. I think so, yes. Okay. So in Lab 6, you're started to implement the modulation part, which is the physical, if you think about the physical layer of a communication system. Okay? So you're developing modulation and demodulation. In part B, you're going to use this and build a layer on top of this, which is called like a transport layer or a link layer. It's kind of mixed AX, so it's called AX25. AX25 is a really old protocol based on X25, and it was adapted for amateurs. That's why the A is for. But it was developed before you had the whole 7-layer of networking that were more substantiated afterwards. So for those of you who have taken 122, right, you'll learn quite a bit on basically those layers in networks. So I do recommend for those that are interested in how this works. But the beauty about this is that since you can separate between layers, you can come up with different implementation that would immediately translate, and you can use implementations of the next layer on top of it. So for example, you can take your modem that you're going to build in this lab and put on top of this TCP/IP, if you really wanted to. Okay, because once you have this ability, then you can just wrap that within and transport, and people have done that with packet radio, which is based on TCP/IP over AX25. In fact, the Linux kernel supports AX25 protocol by itself. It actually has that in the kernel. Okay. So what you'll be able to implement at the end is you'll be able to send and receive packets to other classmates. These are going to be very particular type of packets that you'll be able to decode and encode and decode them. You'll also be able to send and receive APRS packets, which is APRS uses AX25 to do something special. In terms of APRS is meant for mostly tactical, nearby local communication of packets, transfer information of where people are located, where cars are located. If you want to control, like a rescue, for example, you want to know where everybody is in. You want to be able to communicate during events or during disaster. This is mainly APRS is designed for. And it's built on top of AX25. So this kind of uses special AX25 packets. But the nice thing about this is a whole network of APRS worldwide that uses this protocol and has links to the internet as well as commercial implementations of it. So you can buy a radio that's equipped with APRS. Okay, so be able to use this. So you'll be able to communicate with that infrastructure that already exists. And in particular, we put an APRS internet gate in Cori. So the antenna on the roof picks up. It's picked up by the software-defined radio there, and then there's an APRS client that decodes your packets and then sends them to the web, okay, to internet servers. Now, it's all based on AFSK, which you are implementing as we speak. I have to say something about these labs and why I think these labs are so crucial and so important for you. It kind of gives you everything is kind of theoretical in this class, but like you see equations, integrals, Fourier transforms. But when you actually have to implement something, that's where also common sense needs to put into place and understanding actually what is really are we doing. I mean, these are samples, but what does it mean in frequency? It kind of puts this together, and this is why I think it's really important. So that encodes data to at 1,200 bits per second. You're doing this already. This is kind of the equation for AFSK, where this is a binary set of data. Now, by the way, we had a mistake in the lab description. It went from infinity to t. Sorry about that. I put a minus here. But here's an example of, this is an equation that describes something which is, this is kind of a theoretical equation, right? Everything that happened before now, right? We integrate all the signal that we had from minus infinity, which can be, depending on your time scale, what does it mean minus infinity, right? If my system is running for a year now, minus infinity is a year ago. If I just started my system, then minus infinity really is nothing till now, and then now it starts. So it's zero before, right? It just one of the things I like about this lab, you have to kind of exercise a little bit common sense. So you don't want to put in your trapezoid method an initialization to minus infinity, for example. You want to initialize to zero. Okay. Of course, when you initialize any float to minus infinity, it will just become, just gives you infinite all the time. Okay, so this is, I'm glad you're going through this exercise because that will really help you when you get a job. Okay, so you transfer bits now by switching between 1200 hertz and 2200 hertz. Okay, and pretty much that's it. The sampling rate, in particular, we picked a really not a nice one, 44.1 kilohertz, as opposed to 48 kilohertz, which everything kind of divides nicely. Again, you have to deal then with what does it mean half a sample? How do I make sure that I don't have delays aggregating over time if I do packets? You have to go through this, and that's a good thing. This pain is really useful in your in how you grow up to be engineers. Really, it makes you stronger. Believe me. You remember that. Hopefully before the evaluations, but anyway. Okay. All right, so you're implementing two type of demodulator. One of them is a non-coherent demodulator, where effectively, because it switches between two frequencies, you can put filters around those frequencies. These filters are kind of like a match filter, right? Because you're sending a pulse over a certain amount of time over a particular frequency. And this is really what you're doing here. That your bandpass filter is about the size of a bit, right? And this is kind of like a match filter. You're doing it, of course, in a complex, because this is a non-coherent repeater transmitter. We don't know what the phase of the transmitter. So we have to do complex filtering, which basically means that you're filtering with a sinusoid and filtering with a cosine. You're looking at both of them at the same time. The expression is complex, but in fact, practically, you are filtering through a sine, filtering through a cosine, and then taking the sum of square root between them to get the magnitude. Okay, that's effectively what you're doing. So if somebody tells you, there's no complex values, it's like, yeah, of course they're not. You were just modulating by a sine and a cosine. Each one of them is 90-degree phase shift, because we don't know what the phase of the transmitter is. For example, the worst case could have been that you just you use a filter which is just cosine modulated, and in fact the phase was of a sine, and you're completely orthogonal to it. You won't get anything. Okay, this guarantees the fact that you're using both cosine and a sine and taking the magnitude guarantees no matter if you have a sine or a cosine anywhere in between, you'll get the maximum amplitude. Okay, that's what really is. So you're running through one filter, the other filter, and then taking the absolute value, which gives you the envelope, and then subtracting it, and then taking the sign of that. Now, one thing that can happen in practice is because of filtering and all sorts of reasons, maybe the output of this can be higher than the output of this all the time. You can have a bias. So good demodulators try to figure that out and compensate for this. We're not doing this right now here, but one of the things that you could do in the project is try to, improve upon the fact that this might have a bias. Let's say it's always four times bigger magnitude than this one. If that's the case, you might still be able to demodulate in most cases, but if you have some noise, you'll become really sensitive to that noise, as opposed to if they're balanced, then you're not as sensitive. If there's a bias between these two, what it really means is that all this is going to be shifted up. And if you put a threshold of 0, then you're not really putting a threshold in between. Okay, so you're making yourself more sensitive to noise. Okay, this is some point to think about. You're also building an FM demodulator. You're going to compare these two. I don't want to spend too much time on this because you're not going to use it in Part B. You could use it in your project, for example, but in Part B, we don't require you to do this. And then you continue a bit. All right. Okay, so now any questions before we move to AX25? One of the things that you could do in the project, for example, is change the modulation scheme from AFSK to MSK. So you can go at twice the rate. Almost the same bandwidth. Almost. Okay, so that's another option. Yeah.
For the FM1, what we're using a bandwidth of 1.2K, so 500 hertz.
500 hertz on both sides, plus the bit rate.
Yeah.
So you're using about 2 kilohertz of bandwidth.
Yeah. I was thinking when we first built the filter, I was trying to use 500 hertz on both sides and modulate the frequency to 1.7K. So I was thinking that is right, but then that doesn't really give me the right thing. So I have to use the low pass filter of 1.2K first, and then modulate to 1.7K.
Yeah, well, you need to, when you generate the filters, generate them on DC, and then complex modulate them to 2200.
So when I generate DC, what bandwidth do I use?
Oh, you need a bandwidth of about 1,000, I think, or 1,200 or something like that.
Yeah, so why couldn't I use 500? Because
It's too narrow, so it's not going to capture all the signal. Okay, so your signal actually around that frequency is a little bit wider. It's about 1,200. Okay, so what is AX25? It's a link layer packet-based protocol. So it's packets. It's not continuous transmission. Okay, that means that you can use the same channel. Many users can use the same channel. You can think of it as a bus. Okay, that the air is a bus, and then everybody uses the same channel. So you have to be aware of collisions and all sorts of things like this. Okay, so some people, some radios will implement sense. It will sense whether there's a packet being transmitted. If there isn't, then it will try to transmit. Okay. It is based on AX25, and it has a very particular packet formation. First of all, it starts with a flag. Okay, and I explain what the flag actually is. And the flag is 8 bits. Okay, each one of it, that's the number of bytes. Okay, that's the number of bytes. Each byte is 1 bit. Okay, so 1 byte for a flag. It has a destination address, which is in fact, in APRS, it is used to describe the version of the software for APRS, or the version of your radio. Okay, it's not actually used for routing, for the APRS. For AX25, you can use it also as routing information, but this is not used actually for routing. Source address is your call sign. Digipeater addresses tell you basically how your packet should be repeated, and whether it's going to be repeated once or maybe twice the maximum or 3 times the maximum, and that would determine of how far it's going to get from you while it's passing through repeaters. Okay. I'll explain this a little bit later. Control field is just fixed from AX25. It's very particular packet. ID is fixed. You don't need to actually play with this. Information field, that's what the actual information you're sending. And I'm going to explain what you're going to put there. And then it has FCS, which is a field for checksum and error detection. So you calculate some function on the bits here, and you store the values of that function over here. And so when you receive a packet, you're going to go and apply the function on the bits you received and see that it matches whatever has been sent. Okay, and if there's not matching, that means that there's an error, either here or here, but there's somewhere there's an error. Okay. And then at the end, it closes with a flag. Okay, so one thing that they did in yes.
So since we are transmitting our call sign to source address, do we actually need to transmit a call sign before?
No, this identifies you. You don't need to transmit your call sign before. This already identifies you. Yeah, that's a good point. Okay, so when they designed the scheme, they try to make it easy to be able to decode. So there's a few things that are special here. First of all, instead of NRZ, so non-return to 0, so a 1 is a mark and 0 is a space, okay? They switched to a mode which is called non-return to 0 inverted, NRZI. That means that a bit with value 0 is encoded in a change of bits. It's kind of like a Manchester coding. Remember that we talked about this? So it's encoded in a change. Okay? So a change from 0 to 1, from low to high, from one frequency to another, or from the high frequency to the low frequency, that means that bit 0 is being transmitted. And a bit 1 means no change at all. Okay? So if you have a sequence of 110, 11000, it is converted to 11000, 11101. You can actually trace it and understand why is that. So if you have an initial value of a 1, so this is no change, so you store a 1. This is no change, you store a 1. This is a change, so you store a 0. This is a 1, so you keep the 0. This is a 1, so you again keep the 0. Then it's a 0, so you have to switch, so you get a 1. Okay? Yeah.
So how do we know the initial value?
It's 1.
It's always 1.
Yeah. Okay. The other thing that they did is they added what's called bit stuffing. So every 5 ones that you have in the original stream, they're going to put in a 0. The reason for this is that guarantees a signal change after 5 bits length. And that's to prevent, for example, if somebody just wants to send a lot of 1s, then it's just going to be a constant frequency for a really long time. And that's a problem if you want to sync between transmitters. You want to create changes so transmitters can sync to each other. Okay, because there's always offsets between clocks. And so the longest constant frequency that can happen is only 5 bit length. Okay? So 5 over 1200 milliseconds. That's the 1200 in seconds. 5 over 1200 in seconds. That's the longest constant frequency that can always happen in this case. Yep.
Is that enough for clock synchronization?
Yeah, because it happens more often than this, but that will be the maximum. Okay. That will be the maximum. Yep.
How do you distinguish between wanted 0 or 0 that's just put there for synchronization?
It doesn't matter. When you detect it, then you detect, and then then whenever you see more, like you see a sequence of 5 ones and then a 0 afterwards, then you remove that 0.
Well, maybe that 0 was an actual. It wasn't put there.
It actually, this is sorted out. It's actually, no, they cannot be. They cannot be more than 5 ones, so that works out fine. It works out fine because they'll stuff as 0 anyway if there's 5 ones. So there's be 2 zeros if you have a 0 originally. There's just not possible to have more than 5 ones. Okay, so if you have 5 ones, you have a 0 afterwards, so you remove it. Now, the flag, if you now look at this, the flag has actually 6 ones. That guarantees that the flag is unique. Okay, so you can always detect the beginning of a packet by looking at, basically this is a transition, constant, and then transition. So it's kind of like a rect pulse if you think about this. That is a certain length. And so this is how you can always distinguish between the flag and bits. And a packet always starts with a flag and ends with a flag. Okay? So that's the nice thing about this bit stuffing is that in the packet there's, it can never be more than 5 bits. But once you see 6 bits of 6 ones, then you know that the packet ended. Okay? That's how they actually implemented this. Questions? And the reason I'm showing this is because, you have to think about all these things. It's not just the signal processing, right? There's another layer that you have to think about it. But all these have to be connected because you want to make it easy also on the other layer to do things, right? So now I can, not worry about synchronization too much because that is guaranteed in the next layer. But every layer kind of needs to look down and up and create things that it's easy to actually materialize and implement. Okay, so that helps a lot, and you'll see that in the decoding. The fact that you use this non-return to 0 inverted helps a lot. The fact that you have the synchronization helps a lot. Okay, so what is APRS? APRS is built upon an AX25. Okay, it's a ham packet system for real-time tactical digital communication. It's based on AX25. It has many commercial implementation. The national frequency is 144.39 megahertz, channel 117 on your radios. Okay, if you turn it on, you hear like all this stuff. This is packets being transmitted by and digipeated and so on and so forth. Just put on this channel, you hear it all the time. It's like, okay. Like if you play AFSK 1200, you'll hear it. Sounds exactly the same. Actually, it sounds like modem Bell 202. That's how it sounds like. The ISS also has a packet digipeater, and it transmits on 145.825. Okay. There used to be other satellites that also do this, but they're not working right now. There's some that, I don't think there is another one, actually, that you can operate. The cool thing is there's also internet aggregation and services. For example, you can send a packet, and once it gets to an internet link, it will be forwarded to an internet server that will then forward, for example, an email or SMS message, or put your geolocation online so people can see. Or if you have some tactical team that you need to, like you have, I don't know, you're organizing some event and you really need to know where people are, then that's a really good way to do this. The balloon project, for example, that I showed you, they used APRS because it's already there. They can just transmit packets and it will be picked up and aggregated by APRS internet links. So they don't need extra infrastructure to track something. Okay, so that's a really useful thing. By the way, this is a new sending SMS. There's a new service. Somebody had a how do you call this? Public funding on Indigio. Asked for money from amateurs to basically fund this SMS for a couple of years, and he got funded. And now this is running. You can now text message from your computer to your phone now in Friends, okay, through the radio, which is kind of useful, especially if you go somewhere and there's no internet. Text messaging is pretty reliable. Okay, so an APRS packet looks the same, right, like AX25. The destination address, we're going to use APDSP. That's the software version for this class. We're going to be using it, okay? We haven't authenticated it, but we're just going to use this. APRS receiver, only try to decode packets that starts with AP. Okay? If it doesn't start with AP, most commercial products will ignore the packet that you're sending. Okay, so at least start with an AP. Source address will be your call sign. Digipeters, wide 11, comma wide 21, will guarantee that your packet will be digipeated at least twice. Okay, so a digipeater receives a packet, it sees wide 11, wide 21, and then it will remove the wide 21 from it and will send it again. And then the next one will pick it up, it will see wide 11, will remove it, and will not aggregate it any further. Yeah, so it digipeated twice, I think. So something like this. But basically, you remove it removes a number and then it digipeats again. Okay, that's how it works. In the Bay Area, probably you don't want to do 2-1. You're just going to do 1-1 because it's enough. There's so many digipeaters here. If somebody picks you up, digipeats it, it's most likely will get into an internet link. Okay, so just to reduce congestion, probably use just wide 1-1. Control field, that's a type of a specific type. It's called a UI X25 packet, so it's going to be 0.3. That's to be conforming with the AX25 protocol. This is a very particular type of packets. There's other type of packets for AX25, but we're not going to be using them for APRS. And the ID is F0. Which I really don't know what they mean, but you can read the AX25 protocol description if you really are interested. And it's pretty long. Yeah.
So for wide 1-1 and wide 2-1, would you send wide 2-1 alone, or would you send wide 1-1?
No, I think you need wide 1-1, wide 2-1. Yeah. I'm not 100% sure. If you send wide 1-1, it will digipate it once. If you send wide 1-1, wide 2-1, it will digipate it twice. That's pretty much it. Yeah.
What's the limiter you use to separate wide 1-1 and wide 2-1?
Comma. Mm-hmm. Yeah.
How do you pass it?
What?
Like, there's like 7 bytes in the destination, so 5 bytes for the address. Do you put zeros in front or after?
I'll explain this actually, but you put 0, you actually have to pad them. Yeah, you pad them with zeros as well as the source address too. But we actually, so the thing is, we're giving you a way. You basically just put those, and then I downloaded. Someone developed an AX25 for Python, which we use some of his code modified a little bit so it fits to this class. But basically, it helps you create the packets, so you don't need to, create all of these. I'm telling you so you know a little bit about the internals of what you're going to be doing. You're going to get an AX25 library that you'll be able to use. It's actually not that long. If you open it as, it's that long in relatively normal fonts. Okay, what's interesting really is the information field. Information field sends you the information of the packet, but in APRS it's also used to send other things too. It's 256 bytes long. Okay, and there's 3 types of information messages in APRS. There's one which is called message. There's another one called position, and another one called status. Okay, there's 3 types of them. And each one has a different format that given a... Yes? Yeah, sure. Go for it.
Messages, all, at the end of it, message text.
Oh, that's fine. That's why I sent it. That's why I sent. Yeah, that's fine. That's not a typo. Typo would be like massages or something. Yeah.
There was a typo earlier. You said beginning and end instead of beginning and end.
Where?
Back at you guys. Sorry, one more. Black at beginning and end.
Where?
In the third sentence. Yeah, something.
Oh. At beginning, end. Oh, yeah. You're killing me. And remind me?
Max Gorilla.
Again?
Max Gorilla.
Oh, yeah, that's your $2. Pretty good. Yeah, it's worthwhile taking this class. Okay, so type of messages. Am I doing on time? Yeah, I'm good. Okay, so a message starts with a colon. Okay, that's how you know that a message type message will start with a colon. Then there you're going to say who you want to send it. So if you say all, and then you use 0 pad up to 9, I think. Then another colon, and then have your message. Okay, so that's where to, and that's basically the message. Everyone will capture the 64-byte message text. It's 64 byte. If it was text, then it would have been 65. You know, okay. That would have been a typo. Or you can send to me, KK6MRI, and this message would only show on Mickey's APRS-enabled Yaesu VX ADR radio screen. So if you send it to my call sign, my radio would like blink and say, "Oh, dude, you got a message." Okay. Sometimes all will also show. CQ is another one that you can also do. CQ. Email. If you send to email and then you put the address and write what the email, I'll get an email from OpenAPRS with your message, okay, within a few seconds after it aggregates to the internet. SMS gate with at the number will send an SMS text message to that number. That works, right, Frank? Yeah. Because he got a text message. This is a new CQ server is kind of like it's interesting. You basically can create a group. I created when I send the first time EE123, it will create a group called EE123 that everybody that registered that group, then if I send a message to that group, it will send messages that they'll show up on the radios. Okay? So you can send, for example, to CQ server, you can send a question mark, and then CQ server will send packets with which group are now active. And you can get a list of them. So it's kind of like a bulletin board in that sense. Okay, so this is the messages. The other one type of is position. Position starts either with an exclamation point or an equal symbol. It then puts a latitude in 8 characters, slash longitude in 9 characters. Why? You need 9 instead of 8 for longitude. What's the maximum latitude? North Pole is 90-degree latitude. South Pole is minus 90, right? Well, 90 south, right? But what is the most east and the most west? 180, which requires another extra character. Okay, 100. Okay. Okay, so then that's the position. Then you can pick your icon. And you can look for a list of icons, but K would be a school icon, what is this? Bracket will show a person. And if I send this, we'll show a person walking on Oxford and Hurst. Okay? And then if I send this, it will show a person on top of Everest. It's not illegal to do this, but it's just not good form. Okay? And this shows the school symbol on Corey Hall, for example. And then the last one is a status message that some radios will display that. So Kenwood type radios, if they see a status message, they'll display that on, people that pick those packets. And for example, and that starts with a bigger than sign. And for example, I like radios, or you can send in a status message that you're monitoring 146.520, for example. You can send APRS packet if somebody calls you then to that frequency. It's like your Facebook age, right? You know what a status message is. I don't need to tell you. It's like, I feel good. I feel drowsy. I feel sleepy. You know that. Any questions? Yeah? No? Okay. So how do you generate an APRS packet? You import AX25, you call sign, KK6MRI, digipath, you create this string, wide11, wide21, destination APDSP. The info one is this email. This will send an email. If you comment this, we'll send a report, and so on and so forth. And then you call packet equals AX25 UI, and then you put those values, and then you do print packet unparse, and it will unparse the bits. Okay, you will get this. These are the bits. That's the binary bits, so you get a bit array. And the bit array starts with 0, 1, 1, 1, 1, 1, 1, 1, 0. What is this? Flag. And it ends with a flag. What you need to do then is to take this and convert that into NRZI. Okay? To switch it to non-return to 0 inverted. Okay? And I think we even coded that for you. Yeah.
Can you go over again what the difference between flag 1, 1, flag 2, 1 is and why you use flag 1, 1?
Not right now, actually. But I'll be happy later. I just want to finish some of the things that are more important than this. But basically, wide 1, 1, 2, 1 sends twice. Wide 1, 1 sends once. Well, we can talk about it later. Okay, what you're going to do is then decode APRS packets. And because you have this transitions, a limited transition, we did a different implementation than what you did in Lab 6 Part A. We used something that is, there's actually a nice paper that was on QST magazine about decoding APRS. And how they did this is decoded by zero crossing. So you look at the analog NRZI, and what you do then is you look at the zero crossing. So if you see a zero crossing of a certain bit length, this is 1.025 bit length, that means that there's a transition, a single transition. So that's a 0. Then the next transition is 7 bit length. Right? That means that that's a 1, 1, 1, 1, 6 times. And then another transition of 1 bit length. That means that all of this is a flag. Okay? So then if you see 2 bit lengths, that means it's a 1, 1. Basically, it looks, using this transitions, it's really easy just to look at the timings and then figure out how many 1s followed by a 0 there are, up to 5. Okay? And so you can just create a stake machine and then just count and then figure out how many bits and just aggregate them. So it's really easy to figure out when it starts and not. And that's how we implemented this for you, by the way. We implemented this scheme. You only need to give the NRZI, and then that goes through and very simply actually implements this type of decoding. Okay? Yeah, you can see the code, of course. Yeah. Which one? Actually, it's similar. It's similar. It's actually slightly less noise resistance than like a coherent detector that you look at exactly on the, but it's actually pretty good. So it's easy to implement, And this is how we decided to do this. It makes things very simple. The one thing that it solves is the synchronization problem, because this is self-synchronizing. If there's so first of all, we allow for errors. For example, if you know that there should be a bit 0 over 1 bit transition, right? We're going to accept it to be bit 0 even though it goes all the way to almost 1.5. Okay, so it is resilient in that sense to timing error. So any timing on your transmitter, this actually deals with it. So it's a robust method for timing detection too. It allows for some wiggle there in terms of timing. Okay, you're going to be able to think about this a little bit more when you do the lab. This is a packet picked up from ISS that you're going to be first decoding. So you're going to decode this, and that will give you this, effectively, text, once you decoded this. What you really need to do in this lab is to implement a stream processing. So this code knows to work on a whole buffer, like a really large buffer. That will work perfectly. But what you're getting, if you want to do a real-time implementation, you're getting packets of about 1024 bytes. You will need to aggregate them into about 1 second type of size of a packet, and then be able to send that to the decoder to look for packets in it. Then you'll get the packets that comes out, and you'll be able to display them or process them or do whatever you want. But the thing is, you have to make sure that the decoding of these aggregated packets is the same as if you had all the data in the first place. So you have to make sure that filtering is done appropriately between those packets, so kind of overlap and save type of implementation. You have to be careful when you write your own FM demodulator. You're performing some filtering. There's delays there, some valid, non-valid values. Now that you have to stitch these different segments, different buffers, you have to make sure that the receiver doesn't know or doesn't care that it's broken into parts. Okay? Because we're going to do real time. So you'll have to deal with that. And that takes a little bit thinking and some time. Okay? So you need to make sure that there's overlaps. The other thing that can happen is that you take a 1 second worth of buffer, you send it to the decoder. The decoder detects a packet just at the end of the buffer. Right? What's going to do? So what we chose actually is to send you, if that happens, it sends you a message, where did the packet starts in the previous buffer? Then you can take those samples and concatenate it to the next buffer. Okay, but you have to think about that a little bit. This is an example of the GUI application that we built for you. Okay, we wrote a GUI application. Don't have so much experience in GUI programming. This is what came out. Whatever. So live with that. Or you can modify it if you know how to modify a GUI. Go for it, but I'm done. I don't want to touch this anymore. Okay? What it does tell you is, you can put your call sign, the digipath, destination, to call sign. You can choose the devices. It saves it to an INI file. So the next time you do it, it knows it. You can also send beacon. Beacon will send a location message. And you can turn the beacon on every 60 seconds. It will automatically send packets. So be careful with that because it will transmit. And then here you type. You'll see what you typed, and this is what you receive. Okay, let's do a demo, Frank. So this is the application. You also hear the radio. It pushes the... It's not working for you now. Screw it up. Well, it worked before, anyway. So you can hear actually the sound coming out. So that's good for debugging. Yeah? It was running for too long. Yeah, there you go. That's a message from Frank. We transmit at the same time, I think. Of course. So now I transmitted. Do you pick it up? Yeah. There you go. And so on and so forth. And this is, if that is transmitted over the APRS, it will actually be digipeated. So you can do that from your house, and it will be digipeated. So be careful not to, if you have, until you debugged it, don't go to the APRS frequency because you might mess up with other people's systems. Okay? So just be careful. Don't overload it. Don't transmit like for an hour on the APRS frequency and like block the entire Bay Area. So this is a nice application that you'll be able to use. I have a couple of tips. I'm stealing a couple of minutes, but sorry about that. But I just want to give you some tips. This is, by the way, communication with through the ISS that I had last night with KG6NUB. He's from Stanford, so we communicate through the ISS. I guess I could give him a call, but anyway, that was fun. That was quite satisfying. I asked him to, he said very impressive, so that's because I was using a tape measure antenna. Yeah. Okay, so tips for debugging: check the audio device volume on a computer. And the radio. That's the one thing that can screw it up, because if it overdrives it, then it doesn't work. We tried before. For example, some computers some devices put out really loud sound, and that distorts it. So you have to be careful. Okay. Turn the squelch off. So you don't need to wait for the radio to wake up in order to receive a packet. That takes time. The packet's already transmitted. Okay. So if it's on all the time, the radio, then you'll be able to pick up more packets. Create an audio. I found this mistake. It's a loop. And let me show you what I mean by the loop. And this will save you an immense amount of time. Okay? You see the yellow one? Carefully, but really carefully pull out. Okay? You pull this out. You take this. You put in. Whatever you're transmitting, now we'll go to the receiver. And it's a closed loop without the radio. So that will allow you to debug a lot of things, okay? Whatever you're transmitting, you're receiving. And if you have a problem with volume, you'll be able to see it. You'll be able to hear and everything, okay? No RF interference, If it works here, then you're in good shape, okay? This is enough to pass the lab, okay? If you can make that work. Because other RF interference is other issues. But then after